speak about the discrete exterior calculus and its application to computational electromagnetism.
Right. Thank you. First, I'd like to thank the organizers for giving me the opportunity to speak today. I'll be speaking about discrete exterior calculus and its applications to computational electromagnetism, and this is joint work with Mathieu Disbrun, Anil Hirani, and Jerry Marsden. Okay, so let me just give you a bit of motivation for what it is we're trying to do. So one of which comes from computer graphics. So say you're trying to represent a surface like that, and it's like you decide to discretize it using a bunch of piecewise linear surfaces, and then you ask questions like, say you wanted to do image processing based on a PDE technique on this, and so the natural question is, how do you construct differential operators in an object like this? Other times you might care about things like smoothing, simplification, and meshing. So one of the things which matters then is, for example, what the curvature of this object is. So if you're a traditional differential geometer and you're asked what the curvature of a piecewise linear surface is, then the answer is trivial. It's like on parts which are flat, it's 0, and parts where it's like you have edges which don't meet up properly, then it's infinite. Clearly that's correct from some point of view, but not very useful, it's like for computation. And the question is, how do you go about constructing it's like things like curvature operators and other differential operators on surfaces like this? And it turns out that at least in the computer graphics community, there's very little consensus on how to compute even basic surface properties like normals. So other things you might want to do, for example, are computing mean and Gaussian curvature or the principal curvatures of this object. So that's the motivation coming from computer graphics. And it's like, for point of view of simulation, it's like turns out that in electromagnetism, there is an exact sequence property. So in particular, it's like if you take the RAM, it's like sequence, it's like, and you sort of specialize it to 3 dimensions, and you do certain identifications, and you get this grad called div exact sequence, which is relevant in electromagnetism. And these exactness properties are important. It's like for ensuring that your corresponding numerical scheme is stable. So in particular, for example, if you were to try to compute, say, the eigenmodes of some sort of domain, it turns out that if you have schemes which don't preserve this exact sequence property, then you get very bad numerical results. So as an example, you're trying to compute, as I said, the sort of the eigenvalues of some sort of mode, some cavity, and this is done using what is known as compatible discretization. So these are finite element schemes which preserve the exact sequence property. And if you look at the inset here, you'll see that the numerics actually gives you eigenvalues at what the true values are. So those straight lines here, those straight lines are what the true eigenvalues of the object are, and those dots you see here are what your numerics is telling you. Whereas if you would compute this using, say, linear finite elements, then it's like you get a bunch of eigenvalues which basically tell you nothing at all. So the way we're going to do this, it's somewhat idiosyncratic, but that's the way I do this stuff. And it's going to be from the point of view what is known as geometric mechanics. Geometric mechanics really is using differential geometric and symmetry techniques applied to study of Lagrangian Hamiltonian systems. And in particular, we're interested in constructing numerical schemes based on that framework. And so you can construct numerical algorithms from the point of view of geometric mechanics. And as an example, there are what are known as variational integrators, which are obtained by discretizing Hamilton's principle. And they have the nice property that they're automatically symplectic and momentum preserving. So this is sort of well understood. It's like in the ODE setting, it's like, and what we really have to do in order to do electromagnetism is to extend this into the PDE setting. So the missing piece, it's like, which one really wants are things like exterior calculus and connections and principal bundles, and I'll be talking about how one might discretize exterior calculus. Okay. So what's the motivation for discretizing exterior calculus? So as I sort of alluded to early on, it's like in the context of computer graphics, you'd want to construct differential operators in terms of combinatorial operations on some sort of mesh. In this case, it's going to be a simplicial complex and its corresponding dual cell complex. And it turns out that it's useful if you want to really construct a full theory of computational geometric mechanics. And in particular, if you want to derive natural discrete conservation laws. And as particular examples, it gives you natural discretizations of things like div, grad, and curl. All right. So what we're going, some of the basic pieces, it's like, which go into developing a discrete exterior calculus are these primal and dual complexes. Then you'd want to introduce differential forms and the exterior derivative, but At a discrete setting, it's like you want things like a Hodge star and codifferential, maps between one forms and vector fields, and so on. And the applications are to vector calculus, diff, grad, and curl, it's like, and Laplace-Beltrami operator. So the thing which we're going to look at, and the thing which is actually relevant in the context of electromagnetism, is the Laplace-Beltrami operator and its corresponding higher dimensional generalization, the Laplace-Durham operator. And the things which show up, it's like in constructing this are things like primal-dual complexes, differential forms, and exterior derivatives, and Hodge star and codifferential. Okay, so let's talk a bit about primal-dual complexes. And it's like, I guess it might not be so relevant to this community, but to a lot of people in engineering, it's like they might wonder why do you care about these primal-dual complexes? And it turns out that it's really essential for capturing the inherent geometry of the problem. So in some sense, for example, in geometric mechanics, you care about whether something is on the tangent space or it's on the cotangent bundle. And really, it's just that these objects transform in different ways. And it's possible, and it's often done in practice, that people identify these spaces through the metric, but it turns out that at a discrete level, oftentimes this is a bad thing to do. So the corresponding distinction between, say, something being on the tangent space and this cotangent bundle, for example, whether or not these objects live on the primal complex or the dual cell complex. So this is not really a new idea. It's like certainly in the context of numerics, it shows up really often in sort of finite volume methods, finite element methods, and finite difference methods. So as a classical example, I guess to this community it might not be so classical. Let me sort of think about, say you wanted to discretize the fluid equations. And one of the things you could do is to ask, for example, whether, say, a density is, where do you put information about the density? So you could put information about the density at, for example, a cell, right? So you can have the density of a cell, or alternatively, you could put density information at the center of a cell. So as it turns out, there are implicit in this numerical scheme, it's like a staggered mesh. So you have a mesh, a primal mesh here, it's like, and then there are meshes which are in some sense complementary to that. And you put certain pieces of information in one or the other. At other times, these primal and dual things don't show up explicitly. You only have a primal mesh explicitly, but it shows up in the choice of shape functions. So in the finite element setting, it's like what you have is that you have some sort of mesh, and then you approximate, say, these fields over these objects by choices of finite dimensional function spaces, which are composed of, say, these hat maps or these characteristic functions. And as it turns out, in this setting, it's like it's like the choice of shape functions really sort of implicitly introduces a dual complex to this object. So things which are in some sense in the primal mesh are given in terms of these hat maps, and things which really should be on a dual complex but which are not, then take the form of these characteristic functions. And there are certain differential relationships which map from one to the other. Right. So let's see. Another example, it's like which shows up quite often, it's like in the context of sort of ordinary differential equations, is what is known as the leapfrog scheme. So this is a scheme where the velocity information and the position information are based at different times. So let's just say you're sampling a sequence of points. It's like sort of a discrete sampling of the position of a particle. Then it's quite natural to think of them as being sampled as some integer time points. And the velocity, in some sense, you could think of as an average of its, it's like the position information. The difference. And so it might be natural to think of them as being associated with a point at a half integer value. So there are a lot of numerical schemes which have this staggered mesh property as well. So this is an example of something which implicitly has a dual mesh to it. And the reason why, so let me sort of talk a little bit about this. The reason why position is at the integer points and velocity is at the half integer points is because velocity is related to position by a derivative in time. And so in the time axis, so to speak, the velocity should be offset by half from the position. And this kind of idea shows up in more general settings. So if you wanted to extend this to space-time, so in the case of magnetohydrodynamics, for example, in what is known as the ZS2 2D model, you'll see that something similar happens in space-time. And so now you have derivatives both in space and time, and things which are related to each other by, say, a spatial derivative in the x direction have this offset, half-integer offset now in the x direction, for example. So these things show up quite often. So what we're going to do is to look at the context of simplicial complexes. So it's like, you probably all know what a simplicial complex is. It's, so a K-simplex is just the convex half K plus 1 affinely independent points. And then you want to look at the formal sum of these simplices. And this is the means by which we discretize the object in question, the geometry of the object in question. And examples of chains are, well, they're these directed components. So it's like a point would be a 0 simplex. This thing would be a 1 simplex. And this would be a 1 chain. And these objects with the appropriate orientation would be chains of 2 simplices. And then you'd want that this simplicial complex has certain non-intersection properties and that they form a complex in an appropriate sense. So, so that's your primal simplicial complex, and what you want to do then is to construct a corresponding dual cell complex. And the standard way to do this is by using this object here. It's, in some sense, what you do is that you take the barycentric, well, if you were to construct the barycentric duality operator, then what you would do is you take the first barycentric subdivision, and then you sort of pick together the appropriate points, it's like to form the dual object. But here we're using the circumcentric duality operator. And the only real difference is that instead of taking the barycenters, it's like in constructing this object, you take the circumcenters. And the reason to do this has to do with the numerics, and really that when you construct this duality, the circumcentric dual, what will happen is that this dual cell complex will be orthogonal to the primal complex, which would not be the case if you took a barycentric dual complex. So in any case, what it really does is that it takes a K-simplex and maps it to an n minus K cell, okay? And it satisfies this Hodge-Star property, or this property which is analogous to the property which Hodge-Star satisfies with discrete differential forms. So let me sort of just illustrate that in terms of pictures. So what you have is that you have a 0 simplex, for example, that's just a point. The corresponding sort of circumcentric dual of that is the set of points. It's like in, for example, this tet, which is closest to this point as opposed to the other 3 vertices. Then it's like if you took a 1 simplex, or this edge here, then the corresponding 2 cell is just sort of a piece of the normal to that object. And if you had a 2 simplex, the corresponding dual object is just a sort of surface normal. It's like based at the circumcenter of the 2 simplex, and the 3 simplex is associated with a 0 cell. Okay? So this is a generalization of that idea which I alluded to earlier, whereby you have different representations of the same physical object. Yes? Yeah, that's a bad thing. So, okay, so what we do is that we only work with meshes which have the property that the circumcenter is in there. Right. So, but as I said, the motivation for doing this is that so for example, densities, it's like you can associate with either a 3 simplex in the primal complex or a 0 cell in the dual complex. So things like fluxes, for example, which are basically how much, say, fluid is going through a surface, you can either associate with a 2 simplex or a corresponding dual 1 cell, right? So you can either think of a flux going through a surface or a flux being associated with a surface normal, things like that. Okay. So the way you discretize a differential form is that, well, what can you do with a differential form? You can integrate it over a corresponding, it's like, region. And so the natural thing to do is to pair it by volume. With volumes, it's like by integration. So you have this pairing. It's like you think of basically these discrete differential forms as cochains, and then you assign the value of the cochain. It's like by just integrating the continuous differential form which you're trying to approximate. Okay, so it's just, so discrete differential form is just a cochain in a simplicial complex. And you define the discrete exterior derivative by just requiring that the generalized Stokes theorem holds. right? So if you look at this pairing here and you think of this pairing as being related to that integration formula, then that's just really saying the integral of the exterior derivative of some object over the k+1 region is equal to the integral of that differential form over the boundary. So that's just a statement of the generalized Stokes theorem. Okay. So you have the exterior derivative. What else do you need? So one of the things you need is to relate the, is to basically change representations. As I alluded to earlier, you can, if you have some object which is based at a k-simplex, you can associate it with an n minus k cell. So you want to map between these two representations, and the way you do this is the discrete Hodge star. So it maps a k discrete differential form on the primal complex to a n minus k differential form on the dual complex. Okay, and so basically now you have, okay, so this star here is a geometric dual. So that's the thing which I showed you earlier, and this star here is the Hodge star. So this is an action on cochains. So it's really just defined by this relationship here, and it's really just saying that in some sense the average value of the evaluations are equal, and then the codifferential is just defined in the usual way. Okay. So now given these simple pieces, you have all it takes to construct a Laplace spectrometry operator, and for those of you who are not familiar with it, it's really just a generalization of the Laplacian to curved surfaces. And it's a special case of these Laplace theorem operators. It's like in higher dimensions. So you literally write down the definition of the Laplace spectrometry operator. It's like in terms of, in the usual form, in terms of the exterior derivative and the codifferential. And because you're only working on fields, it's like one of the terms disappears. You're only working on scalars, so one of the forms disappears. And then you expand everything in sight. You see this codifferential here, and you use this definition here to write it in terms of the Hodge star and the exterior derivative, and you really just, it's just substitution. You expand it until you finally get this object here, and what that's really saying is that it's some sort of weighted sum of the differences of the scalar function based at the center point, and it's like at all these other points here. So there's an appropriate weighting. And this recovers a formula using cotangents that's like found by Meyer et al. It's like these are people in the computer graphics community, and it satisfies a certain variational identity. Basically, this is if you were looking for basically simple approximations of the Laplacian, which are sort of weighted differences in some appropriate sense, then this is the one which minimizes the error which you make.
You have weights on your vertices?
Yeah, so these things here are weights. So these are the metric dependent terms, right? Yeah, so they're all sort of hidden there. Yeah, so they're weights. It's geometry, not topology in this case. So then what you do is that, okay, so that's the Laplace spectrometry operator. It's like, and then it's like, in order to do electromagnetism, you need the wedge product as well. And it's really sort of an appropriate anti-symmetrization of the cup operator with appropriate geometric weights as well. And so it's a purely combinatorial definition of the wedge product, and it also comes in these dual variants as well. So this is just the expression for the wedge product of two primal differential forms. So, and it has a property that's anti-commutative. It satisfies the Leibniz rule, and it's not associative in general, but it is associative for closed forms. So you might say, well, what good does that do you? And it turns out that the good it does is that associativity for closed forms is enough to ensure that in the limit, it's like it is associative. So it is non-commutative in general, well, it's not associative in general, but in the infinitesimal limit, it is associative. So let me just skip that. So that's a bit about the geometry. Let me talk about how you go about discretizing the mechanics, and then go back to saying how you can do these kind of ideas for, on first case, harmonic functions, and then it's like more generally for the Maxwell equations. So the motivation for doing this from the point of view of geometric mechanics is that in a lot of problems of interest, basically there are properties which are conserved by the flow, in particular things like the energies. You might have symmetries, reversibility, monotonicity, for example. Other times you have momenta, so the familiar angular linear momenta. If you're doing fluids, there are things like the Kelvin circulation theorem, which come from particle relabeling symmetry. If you're working in Hamiltonian systems, then you have a symplectic form. If you're interested in integrable systems, you might want to preserve integrability as well. Other times, the equations themselves evolve in a nonlinear space. So as an example, if you wanted to look at rotational dynamics of a rigid body, then really this is something in the rotation group, and the rotation group is in a linear space. So the question is, how do you do numerics on this so that it stays in these nonlinear spaces as well? Okay. So what's the motivation for preserving these kind of things at some discrete level? And a real motivation is structure preservation for long-time stability. So the intuition is the following, that these discrete conservation laws basically give you long-term numerical stability. And the reason for this is that you have an object which should be exactly preserved, and you have some discrete object which is exactly preserved by your numerical scheme. And this discrete object is always close to the object which you really care about. And so indirectly, you've shown that the continuous object which you really care about is almost approximately, well, it's preserved approximately for indefinite amount of time. So let me illustrate that in a picture. So this is sort of a naive way of thinking about energy stability for symplectic integrators. So you might have heard that symplectic integrators, it's like preserve the energy for exponentially long times. And the idea is the following: if you have this green energy isosurface, which you want to stay on, so this is the exact energy isosurface, what happens with a symplectic integrator is that it doesn't stay on this, but it stays on something which is perturbed. So it basically exactly preserves a slightly perturbed version of the energy. And the isosurface associated with that is going to sort of wiggle through the true thing. And because this wiggly thing is always close to the green object which you want to be on, as a consequence, you always stay close to that green object. Okay? So this is a nice way of showing that your numerical scheme has certain global near conservation properties, and it's typically difficult to do otherwise. All right. So you see this. So you might say that, well, you know, it's like I don't really work with Hamiltonian systems. It's like I'll work with non-conservative systems. What good does this buy me? So for conservative mechanics, it has the right properties that there's an energy error, but it's always bounded. And if you apply this to dissipative mechanics as well, it's like then it tends to track the energy decay a lot better as well. So this is something which we don't understand at a theoretical level why it works that way. But sort of one intuition is that if you think of these schemes as a splitting scheme where you first split the vector field into the Hamiltonian component and then perturb it with the dissipative component, then what's really happening is that your numerical scheme is not introducing any artificial dissipation except that which is coming from the physics itself. So more or less that's the reason, at least in a hand-wavy way, why you would expect that these numerical schemes do better even for dissipative systems.
What problem is being graphed there?
Oh, it's just a simple, it's like point mass. It's just a point mass. Yeah.
What does that mean?
So it's just a particle. It's like, say, a mass spring system. Yeah. So, so it's fairly typical. Okay, so I guess let me just mention why it is that people end up working with these these numerical schemes which are dissipative. And the reason for this is that in numerical analysis, the typical thing one does, it's like one cares about in your numerical scheme is that it's stable, which is to say that if you have a linear problem which is non-oscillatory, which is not growing, it's like you want your solution not to grow as well. So you look basically at the eigenvalues of your discrete operator, and you require that it's not off the map, and you require that it's within the unit circle. And what ends up happening is that in practice, the way you do this is by introducing artificial numerical dissipation. So in a lot of numerical schemes, there's artificial numerical dissipation built into this so that you don't get these spurious oscillations. And so typically it's like for really long time simulations, then it's like these dissipative terms really has a fundamental effect on sort of your global energy behavior. And so that's why they dissipate. Okay. So as a simple motivation for this, so there's the standard. So I'm going to look at solar system dynamics, and there's the standard Ford-Euler approximation to the equations of motion. There's inverse Euler, which is implicit in position and momenta. So Q is position and P is momentum. And there's a symplectic Euler method, which is explicit in position but implicit in momentum. So from the point of view of numerical computational cost, then Ford-Euler is the cheapest, symplectic Euler is somewhere in between, and inverse Euler is the most expensive. Okay? So let's see what happens. It's like if you apply it to solar system dynamics, and it's Ford-Euler is not very optimistic about what happens to the universe when the solar system anyway. So it's like it starts going its merry way. It's like, and then it's like, hopefully that's not Earth here, but it's been voted off the solar system apparently. So you see here the energy error. It's like it sort of increases quite dramatically sort of towards the end. And you might say, well, that's Ford Euler. It's not unconditionally stable, so maybe it's just a stability issue. So let's see what happens with inverse Euler. Inverse Euler is even worse, as it turns out. And the reason why it's worse is because inverse Euler is in some sense dissipative. It's like this orbit. Why is my computer so slow? Okay, so it's, let's see that again. It's somewhat dissipative, and this orbit's sort of decaying. It's like until it's really close to the sun, and then it gets kicked by sort of numerical noise. And so you'll see that it turns out to do quite badly as well. And let's see what happens with symplectic Euler. And so you have these nice sort of nearly closed orbits. And you might say, well, the solar system is chaotic. Why in the world do you have these closed orbits? And it's, well, yes, it is chaotic, but it's not chaotic over these timescales. Okay, so, and you see here that there's a very nice energy oscillation as opposed to serious energetic drift. So that's sort of just motivation for why it is you might want to develop numerical schemes using sort of this approach. And let me just sort of say what this approach is. So this approach is what we call a discrete variational principle. It's based on looking at Hamilton's principle, and Hamilton's principle basically says that if you have an initial configuration and you want to go to a final configuration, then the configuration, the trajectory which the particle takes is the one which minimizes the action. So the action is the difference of the kinetic and the potential energy. And so if you're on the true trajectory and you perturb the curve slightly, then the action is going to be stationary with respect to that perturbation. Okay, so if you want to discretize that, you would do it in quite a natural way. You would approximate that curve by a bunch of discrete points, and then you approximate the action by what is called a discrete Lagrangian, and then you want to perturb these internal points, and you want to require that the action is stationary with respect to those perturbations, and this gives you what is known as the discrete Euler-Lagrange equation. Now, the nice thing about it is that if you construct a numerical scheme in this way, then it's automatically symplectic, and it preserves momentum as well. Okay, so that's the ODE setting. Now we want to generalize this to the PD setting because we were interested in looking at electromagnetism. So instead of just looking at one independent variable, now we look at basically the base space, which is going to it's going to represent your space-time. So it's going to be n+1 dimensional space-time. So you can think of spatial directions and time directions. And then you have a configuration bundle which maps basically so the space of fields back down onto your base space. And then the configuration is something which is just some section of this object. And then instead of the tangent space to this manifold, you'd want the first jet extension. So it's basically all the partial derivatives of those field variables with respect to your space-time coordinates. Okay? And then it's like instead of a Lagrangian, you have a Lagrangian density which maps the first jet to a n+1 space-time differential form. Okay? And with this Lagrangian density, you integrate it over space-time, and that's your action. And then you would require that this action is stationary. So that's the natural space-time generalization. And instead of it being symplectic, as in the case with ODEs, it's like it is now multisymplectic. So there's a multisymplectic form in space-time which is preserved by this object here. Okay, so let's go back to harmonic functions now. So you'd want an inner product. It's like for forms, and it's just given by the usual thing. It's like you take the wedge with the star. And so this will, so if alpha and beta are K forms, alpha here is going to be a K form, star beta is going to be n minus K form. You wedge them together, it's going to give you an n form, which you can then integrate over the whole space, right? So at a discrete level, you want to approximate this, and this is one way of approximating it. And what happens now is that you want to look at the variational formulation of harmonic functions. And you write down the corresponding discrete Lagrangians, just given by this. So if you look at the, so basically, if you look at the inner product applied to d alpha comma d alpha, which is what this is, or df comma df, then you get the Lagrangian for harmonic maps, harmonic functions, and then you look at the corresponding all Lagrange equations, and it turns out that you have this expression here. Now, of course, you can characterize harmonic functions either in terms of functions which vanish under the Laplace Beltrami operator or in this variational setting. And it turns out that whether you do it in this variational setting or you do it in terms of the Laplace Beltrami operator, which I introduced earlier, these things are going to be equivalent. Okay? So a similar thing happens in discrete electromagnetism. So what you want to do with electromagnetism now is to take a covariant formulation using the 4-vector potential as your fundamental variable. You do a 3+1 tensor product discretization, which is to say that you discretize the spatial component using a simplicial complex, and you discretize time by just taking time slices. So instead of having a simplex now, you have these prismal-like objects. So it's sort of a simplex in just the space direction, but the time direction is just an interval. Okay, so it looks like a prism. And the other wrinkle in the problem is that in the construction of the Hodge star operator, you implicitly had metric information in there. Okay, and so the problem is that when you do electromagnetism now, you don't have, it's like you don't have a standard metric structure, you have a Lorentzian metric. And so this converts your Laplace Beltrami operator, it's like into a hyperbolic operator. But if you do the same thing you would do for harmonic maps, it's like you would end up getting the discrete Euler Lagrange equations for this problem, but now in the multi-symplectic setting. And then this gives you a way of discretizing electromagnetism. Okay, so so in particular, the wrinkle was in the Hodge star, and it's because what you see here is that the metric comes in, it's like a definition of the Hodge star. And so in practice, on these prismal complexes, it's easy to write down the effect of this. It really just corresponds to a change in sign. And so there's this kappa, it's like sigma k term, which is what we call causality sign. And it's related to whether it's like your simplices or your cells, it's like space-like, time-like, or light-like. And so these are examples of what that sign is. And it's like, and if you were to just modify the Hodge star in this way, then you would get Maxwell's equations in this setting. Okay, so, right. So then the general question is that, do these operations in general commute, right? So if you have a Lagrangian, it's like, and you can discretize the Lagrangian using this discrete formulation of exterior calculus to give you a discrete Lagrangian, and then look at variations to give you the discrete Euler Lagrange equations. Alternatively, you could just look at the Euler Lagrange equations and then discretize it using DEC. And do they, in general, they don't give you the same equations, but then the question is, when do they do that? And as it turns out, for harmonic functions and electromagnetism, they do. But the question is, when is this true? So all this is part of a more general program, more general research program. So it's like there's an effort right now to discretize geometry. So we just talked briefly about discrete exterior calculus. If you want to do reduction theory, it's like from the point of view of geometric mechanics, then you need things like principal connections, discrete tensor analysis, and so on. And you want to discretize mechanics using these sort of discrete analog of reduction theory. You'd want to construct numerical schemes which automatically stay on these nonlinear spaces and so on. And the motivation from the point of view of engineering is that there is a rich field, well-developed field of control theory known as geometric control theory, and it's interested in nonlinear control, but from the geometric point of view, and it's really based at a fundamental level on the perspective of geometric mechanics. And so by discretizing these objects at the top, the hope is that you could construct good numerical schemes for geometric control as well. So let me just summarize by saying that what we've really done is to incorporate discrete forms, vector fields, and its related operators. And this gives you a way of constructing, as an example, certain canonical discrete differential operators. And you can apply it to, in particular, the Laplace-Durham operator. You can look at harmonic maps in this setting, and you can look at electromagnetism as well. So all this stuff is really on a piecewise linear, it's like complex. And then the question is, there's a way to generalize this to some sort of C infinity kind of thing. And so what we're exploring right now is to look at subdivision surface techniques. So these are ways of generating sort of increasingly refined complexes using subdivision. And what you'd like to do then is like you'd like to show that your discrete differential operators commute with the subdivision operator. And if you can do that, then what will happen is that you will get a natural C infinity generalization of this, even though you're only working on the coarsest level. So Another thing which would be interesting to look at from the point of view of exterior calculus is to look at a fully covariant formulation of electromagnetism. So our formulation is not fully covariant because you've assumed a space-time slicing of space-time. So you've decomposed space into a space direction and time direction, and that's just to make your life easier when you're constructing this Hodge-star operator. But you'd like to consider, say, arbitrary space-time meshes, say a simplicial complex on space-time itself as opposed to this artificial setting. And so that's kind of something which you'd like to be able to do if you wanted to then extend these ideas to, say, general relativity as well. So I think that's pretty much it, if I'm not mistaken. Yep, so let me just end there.